Okay, folks, welcome to today's Authors at Google session, where we've got Alex Bellos, who's going to tell us about some adventures in Numberland. So it's really great to have you here, Alex. A little bit of an intro. Alex studied mathematics and philosophy at university, but he started his career as a journalist. And I read with great interest in the intro to the book. So eventually moving to Rio as the Guardian's South American correspondent, and he's since presented a 5-part series on Brazil for the BBC called Inside Out Brazil, and his short films about the Amazon have been broadcast on the BBC and lots of other channels like More 4 and Al Jazeera. He's written other books, and one of these I was particularly excited about. So he's written a book called Football, The Brazilian Way of Life, and the one I was particularly excited about, ghostwritten, Pelé, the autobiography. And today he's going to tell us about some of the ideas in his latest book, Alex's Adventures in Numberland, which you all have a copy of. So, Alex, it's great to have you here, and I'll hand over to you.
Right, thank you. It's great to be here in St James's Park, near Victoria. So yeah, I'm Alex Bellos, and I write about maths. And not a lot of people write about maths, because I think right from kind of school age, we're sort of divided into people who are kind of the math and numbers people and the words kind of literature people. And I think that's a false dichotomy. And I think that we need to be much more aware of the fact that sort of maths and science is actually part of our cultural heritage just as well, just as much as it is our scientific heritage. And in this spirit, here's a conundrum for you, which links both numbers and words. And it is, if all numbers were listed alphabetically, what number would come second? Now, normally, I'm at literary festivals talking to kind of literary folk, and they never get it. It's actually quite simple. And for you guys to be here, you probably had to do, those famous kind of Google questions, which are really difficult. So this is far too easy. So I'm going to add an extra thing. I want the answer in French. So I'll get to the answer at the end of the talk. Now, I qualified as a journalist, but before that I was a mathematician. So when I came to write about maths, I started to write about it as a journalist. So really, as if I was a foreign correspondent in the world of numbers. And being this foreign correspondent, I traveled sort of back in time to tell the history of maths. I also made geographical journeys. So I went all around the world. And I spent a year or so going around the world. And I went to Japan, which I'll go into later. I went to India. I went to France. I went to Germany. Always trying to meet people whose lives bring out maths in some interesting way. I went twice to the States, but I went across. I went to the West Coast, the Midwest. I went to the East Coast. For instance, I went to St. Louis, Missouri, to meet the president of the American Dozenal Society, who's campaigning to introduce 2 new digits to our 10-digit system, decimal, obviously. So you would count 1, 2, 3, 4, 5, 6, 7, 8, 9, dec, which is a single digit, L, which is a single digit, and then do, which would be 1, 0. And that was interesting, and he actually uses that in his work during architectural drawings, because obviously if you go up to 12, you can divide into 3 and 4 much easier than you can if you're decimal. I also went to Reno, Nevada, to meet the man who sets the odds for most of the world's slot machines, because most of the world's slot machines come from one company based in Reno, and there's a chief mathematician there whose job it is to make sure that all the maths is correct. And so that's a great way of kind of bringing why maths is relevant. And also, the history of probability really begins with gambling, so it's interesting to go and speak to someone who is at the kind of cutting edge of gambling. And also, I went to Scottsdale, Arizona, to meet Jerome Carter. And the reason I went to meet him is that he is a modern-day Pythagorean. Pythagoras is the most famous name in math. Pythagoras is also the oldest real person, as in, Adam and Eve didn't exist, or just ideas, maybe they did, but the person who we learn at school, who is the oldest living person, who we know definitely existed, is Pythagoras. And I thought this is kind of interesting, because surely the oldest living person we should be studying maybe in history. But no, Pythagoras is really before anyone we really learn in history. Now, Pythagoras is famous in maths for the theorem that bears his name. The square of for right-angled triangles, the square of the hypotenuse is equal to the square on the other 2 sides. Turns out, Pythagoras probably didn't invent this. Certainly it was known before him, and the earliest proofs come from China. Also, if you kind of look into what he was and what he did, it's a sort of fascinating story that he's a little bit like kind of Jesus, in the sense that he was a spiritual and religious leader who didn't write anything himself, but over the following centuries had lots and lots of people write about them and kind of raise them to this sort of almost divine figure. And that's essentially why several hundred years after he died, he was sort of almost attributed the Pythagorean theorem, because then he was the guy who made maths mystical. And that's what I found fascinating when I was researching Pythagoras, is that he is both the earliest name in maths, are responsible for maths, but really what he did was he invented anti-maths, because he thought that numbers were not just numbers, but they did not just represent quantities, but also represented qualities. So 2 was feminine, 3 was masculine, 5 was the union of them both, so the most spiritual number. And this mysticism that we really can sort of date back to Pythagoras, as influential as his sort of mathematical legacy. So lots of sort of gematria, which came afterwards, the Masons, all kind of has this sort of Pythagorean basis. In fact, the Masons is essentially modeled on the Pythagorean Brotherhood, which was the sort of cult-like group where Pythagoras lived. So the reason I went to see Jerome is that he is a numerologist. You go to him, you pay lots of thousands of dollars, and you tell him what you're called, you'll give him your date of birth, and he will advise you based on the numbers. And I don't believe anything he really said, apart from one thing, which was, most fortune tellers are poor. That makes no sense, which is true. And he is not poor, and he gets money from being the sort of number clairvoyant. So he said that he advised Puff Daddy to become P. Diddy, and then just to become Diddy, and was paid thousands for that. He also advised people like Mike Tyson, Jay-Z, and spends all his money on motorbikes and has this kind of trophy wife, this sort of amazing condo. And I thought, well, if this was expensive, maybe I could get some advice. It'd be pretty good. So I said, okay, I'm called Alex Bellos. Good name, bad name? And he said, well, what's your real name on your birth certificate? And I said, it was actually Alexander. And he went, you might be quite successful as Alex, but not half as successful as you will be if you change your name to Alexander. I said, why? And he said, come on. One of the greatest men in the history of civilization was not called Alex the Great. And so I thought, well, that's not a mathematical reason. And then he actually showed me, he wrote down all the numbers, and R is a very good letter to end a name with, and X is a terrible name to end a name with. So I actually thought in my book of maybe changing my name to Alexander Bellos, but then actually people might start to think that I actually believe in this. And I have been criticized for sort of giving people like this too much space in the book. But actually, I think anything that encourages us to think about numbers in any way at all is all good. Numerology talks about magic numbers and spiritual numbers and lucky numbers. 3 especially, 3 is the magic number. Now, 3 is a magic number. 3 is very special. And if you think about it, why do we always want to know the top 3? And why in the podium places are there just 3? Why not never the top 2 or the top 4? Just say you're in the school playground. What are your 9 favorite bands? So they're going to be top 3, top 5, top 10, top 100. It's obvious why 110 and 5 are numbers that we like to round up to, because it makes anatomical sense. But why 3? Well, 3 is the largest number, it's the largest grouping that we can understand without thinking. And this leads on to the science of numerical cognition, which is essentially the science of staring at dots and working out how long it takes you to work out how many numbers of dots. So the simplest experiment, numerical cognition, which has been done for decades, is just this. I show a dot to someone who's wired up to a timer, and I say, how many dots? And the person will say 1. Instantly you say 1. Instantly you say 2. Instantly you say 3. But you don't instantly say 4. There's a little delay, and it goes on. That's like 25. You'd never get that instantly. But the moment that you start to actually have to count, rather than something where it is subitize, is 4. So, why is this interesting? It's interesting culturally. So this is contemporary Chinese, ancient India, and ancient Rome. Because 1, 2, and 3 we instantly see without counting that's 1, 2, or 3, they're perfectly good as symbols. Whereas because 4, we have to count them, terrible symbol. So there are other symbols. And this is, I've just chosen 3, but there are other writing systems where it's exactly the same. Now, I was giving this talk once in this sort of grand kind of room, and there was a great antique clock, like right there, and it was in Roman numerals. And as I looked up, I thought, the 4 was I, just completely contradicting what I was saying. But actually, I kind of knew that, and the Romans did sometimes put I on their clocks, because the position tells you what time it is. You don't actually need to read the number, and that would be for aesthetic reasons. And whereas at the beginning of Rome, they did use I, towards the end of the Roman Empire, it was always IV. Now let's look back at India. So about 1,500 years ago, in some parts of India, this is the symbols for 1, 2, 3, and 4. Now just imagine you're writing that without taking your pen or whatever they used in ancient India off the paper. You get that, which is the origin of the digits we use today. So even though we call them Arabic numerals, they actually got to the Arab lands from India. We should call them Hindu-numeric numerals. But the reason why we use Hindu-numeric numerals, why that we use the system that came from India, isn't because of this sort of funny little trick. It's because of the number 0. So, the joke is, what did India give the world? Nothing. Well, actually, giving the world nothing, the mathematical 0 was probably the greatest conceptual leap, possibly in all of mathematics. It permitted arithmetic to be done by sort of the common man. It really meant that quantitative science could begin, and actually it made sort of arithmetic and numbers really be part of maths, because the Greeks didn't have a 0, so basically Greek mathematics is it's all visual, it's all geometric. So being a journalist, I thought 0 came from India. I need to go to India to try and find out why. 1,500 years too late. So I went to meet this guy here, who is the Shankaracharya of Puri, who is one of the most spiritual men in India, one of 4 Shankaracharyas. He has a temple, one in each of the north, south, east, and west, and his is in the east. And millions and millions of people kind of follow him. And it was quite difficult to get an interview with him to talk about numbers and maths. He actually has published some books on maths and numbers, but when I did, it was fascinating. So I went there to Puri in the Bay of Bengal, and was told, because you're going to meet him in a spiritual place, you can't speak English to him. You can only he can't communicate in anything but Hindi, even though he speaks fluent English. So I had to go, which is quite a good trick. So I had to go and speak to the disciple in English, then he would translate it into Hindi, then it would come back, then it would come back to me. So it's kind of like Chinese whispers. I would say something very simple, how is maths linked to spirituality? And then he would translate it into Hindi. It's like kind of learning about geometric progressions, 5 times longer than what I'd originally said, thinking, strange, why it's so much longer in Hindi. Then he would reply, taking about 10 minutes to the reply, and then the reply being translated to me was about 20 minutes. It was a huge amount of time. So I actually had to go and see him 4 times, and each time the sessions went on for hours, and I would just say this one question, and it would come back, and I realized that I was getting absolutely no answers at all from this. And that actually, to try and get kind of a rational reason in a sort of spiritual context, it's completely the wrong way to go about it. And so I just started like zoning out and sort of staring at him. And I'd learned a little bit about him. He wears the same saffron robes every day. He eats the same curry every day that doesn't have any spices in, to be a kind of as bland as possible. In his room, he has no possessions. And what's funny is that when you meet him, you give him gifts. But as soon as he gets a gift, he just gives it to someone else. So if you're lucky to be sitting, there was maybe 100 of us sitting, having an audience with him, gradually you sort of fill up with goodies, because anyone comes and gives something, he just gives them straight back. And it was just contemplating this that I realized that he himself is sort of embodiment of 0, of nothingness. It's all about realizing that nirvana is a state of nothing. It's nothing, so that having nothing is actually having something. And the reason why 0 was invented, the mathematical 0 was invented in India, is that it was a mathematical interpretation of what was a metaphysical idea. And I've talked about how we got 1, 2, 3, and 4. The symbol for 0, which comes from India, I mean, I used to think as a kid, why do it was 0? 0, it's sort of nothing. It's like a hole maybe with nothing in it. Well, that's completely to misunderstand the point. 0 is the eternal cycles of the faces of heaven. So it's kind of infinity and also 0. And it's this sort of spiritual idea linking infinity and 0 and somethingness and nothingness, which is why the Indians, India was the culture where mathematical 0 first appeared. As well as mathematical 0 first appearing in India, this recently appeared. It's the first 0 currency note. And I thought it was absolutely fantastic. And I don't know if they realized the mathematical history of India, but the reason why the 0 rupee note was invented is there's lots of corruption. And so an NGO printed loads of these notes, so that if you want to be bribed, you would just give someone a 0 rupee note to like make a point. Now, our numbers come from India about 1,500 years ago. That's where the 0 was invented in the sort of the system that became ours. Before that, there were numbers. There were Roman numbers, there was Greek numbers before then Phoenician numbers, way back to the first numbers. And the first numbers are about 6,000, 8,000 years old, and emerged in Sumeria, in Sumer, which is now in present-day Iraq. They emerged because people needed ways to count things without actually just using a one-to-one correspondence, say with like pebbles or stones. So just say you were, or notches on wood. So just say you were a shepherd and you had 50 sheep. Before numbers, there's no way of saying you've got 50 sheep apart from maybe having 50 pebbles in your pocket or a staff with 50 notches on. And then they thought, well, why don't we make these little clay pieces, or they didn't think this sort of emerged, they did these clay pieces with different patterns on, and each pattern referred to a different amount. So just say you had 50 sheep, you could make this pattern, say, well, this is how much I've got. So it's much easier for keeping track of your stock and also for doing trade. And that really is the big, those were the first things that you can call numbers, which is a system of words and symbols for numbers. And what's interesting is that as well as being the first time that words and symbols were used for numbers, it was the first of any scripts. So all literature, or any of the Western writing systems, emerged from these first kind of Sumerian accountants, really, developing this system. Now, before they had the system, humans would be able to tell the difference between one thing and two things. It's just that we didn't have the words, the abstract nouns, and the symbols for 1 and 2. So what is it that numbers bring us? Because most people think, well, numbers, they're so natural, they must have been here sort of forever. Well, no, 6,000, 7,000 years in the history of civilization is really not very much. And they are new, and it's because they combine two different things. They combine, anyone who's studied sort of the philosophy of maths or maths will know all of this, but most people, I think, are quite surprised because they think that you can't make anything simpler than a number. It's obvious what it is. Well, it's not. You can divide it. It has two separate parts. It has cardinality and ordinality. Those are just the sort of long words for amount and position. So the cardinality of the number of chairs in the front row is going to be 5 because there are 5 of them there. But when I say count to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm not counting things. So 5 is literally just what comes in the position after 4 and before 6. So I was thinking, well, how can I bring this out to sort of explain that it's not obvious, that these are two very different things. And then I realized that there are some non-humans who have been taught to count, and they are chimpanzees, and they're in Japan, and so I called up the travel agent and flew to Japan to meet these chimpanzees. How do you teach a chimpanzee to count? Well, you have to teach the cardinality of a number and the ordinality of a number. In the early 80s, when Japan was sort of pioneering in touchscreen computers, they got a chimpanzee called I from West Africa and started to teach her both the cardinality and the ordinality using these touchscreen computers. It's always reward driven. You set a task, and if they get it right, they get a bit of food, like shoots down the side. If they get it wrong, they don't get the food. So they end up only wanting to do what gets them food. So that's how they work it out. And for cardinality, what would happen? They would be shown, sort of, say, different boxes with, say, different numbers of carrots or coloured pencils in, and they would have to then tap the symbol for the digit of how many was correctly referring to that. And also vice versa. They'd be given a digit, say 4, and they'd have a selection of boxes with different objects in. They'd have to tap the box which corresponds to number 4. didn't take very long for I to learn how to do that. Ordinality, what they would do, they would show 2 digits, say 6 and 7, so single digits between 1 and 9, and the chimpanzee had to learn to press the lowest one and then the highest one in order to get the food. They learnt that pretty quick as well. So it was in the late 80s, you could say that there was a chimpanzee who had learned the Arabic numeral system because had a working functional knowledge of both cardinality and ordinality. Then the chief researcher there realized we've not taught the chimpanzee 0. Why don't we teach the chimpanzee the cardinality of 0 and then see if the chimpanzee can work out where the 0, what the ordinality is. So for us, it's just like dead easy. Yeah, it's below 1, it's less than 1. So yeah, it's going to be 0 is before 1. 1 is more than 0. We get that, it's obvious to us. So is it obvious to a chimpanzee? So what they did first, they taught the chimpanzee the cardinality of 0. When there's a 0 there was the box with nothing in. When there's a box with nothing in, it was the 0. And then they did the ordinality test. They showed 2 digits, of which sometimes one was a 0, and they waited to see which number the chimpanzee would touch first. Often I kind of hesitate when I say chimpanzee because I want to say monkey, but chimpanzee isn't a monkey because they're apes, and apes and monkey are very different. And once when I was there interviewing these people about it, I accidentally referred to one of their chimpanzees as a monkey, and my God, it was ugly. Because when you work with chimpanzees, because they're so close to us, they're called students, and the lab is called a classroom. It's kind of weird, but it's kind of brilliant too. So they taught the chimpanzees the cardinality of 0, came to the ordinality, did it a bunch of times, and then did the average amount of times of when the chimpanzee, of which numbers they were, and when it was the 0 was tapped first and when it was tapped second. And where was 0? It was between 6 and 7. So even though they understood the cardinality of 0, they had no idea of that's where it was. On the underline, on the number line, it's less than 1. So they did this test more and more and more, and obviously because they're getting food when they get it right, they're kind of learning. And so gradually, the position of 0 on the number line got less and less and less and less, but it never really got below 1. It was always, they were always confused about whether 0 and 1 were sort of more or less the same thing. And that, I think, really shows that what makes it distinctive for us humans is that we could slip between cardinality and ordinality very easily, and chimpanzees cannot. But while they cannot do that, the Primate Research Institute in Kyoto, in Inuyama, but it's linked to the Kyoto University, now they've got about 15 chimpanzees that can manipulate numbers amazingly well. And they thought, well, let's try and use these skills to see if we can find out anything else about the cognitive capacities of chimpanzees. And what they found was that in some cases, they'd never thought this before, chimpanzees have a higher cognitive ability than humans when it comes to the memory of numbers. So what I'm going to show you a clip. And what's going on here is that 5 digits appear on the screen, and then after, when they first did the test, for 0.65 seconds, they're on the screen. So you can see them for 0.65 seconds, then they become white blocks, white squares. What you've got to do is remember the order, the numerical order, and tap them to get the reward. Now, at 0.65 seconds, humans can do it, chimpanzees can do it. So they did it less time, 0.45 seconds, no, 0.43 seconds, sorry. Humans are starting to get confused. They can't do it so well. They can still do it kind of all right, but it makes no difference to the chimpanzee. Still, they get it right most of the time. Then they went down to what I'm going to show you now, which is 0.21 seconds. And now humans really can't do this. But chimpanzees, they can, as you can see. Now, I think I need to press play. So what's going on here? That's the chimpanzee's head. You're going to press that. That's not a 0. That's the button to start. You're going to see 5 digits for only 0.21 seconds. And then can you remember their order the way that the chimpanzee does? And the food's coming down here, which is what's going on. Oh, hang on. Oh, the sound isn't. press the button. It's completely right. And it's also interesting, the chimpanzees, when they do that, they want to have their heads as close to the screen as possible. When humans do it, you kind of want to have a bit of distance. And this was amazing. No one really believed that chimpanzees could do this. And that was a couple of years ago, 0.21 seconds, 5 digits. They can now do 5 digits at 0.09 seconds. That's more than twice as fast. Or 8 digits at 0.21 seconds. So completely amazing. One day, something else happened. They were doing the same test, which I'll show you now. It's also quite interesting. The same test, but 0.21 seconds. He's pressing it. He'll press it, does it. And then the chimpanzee hears something and turns round. So for 10 seconds, it's not looking, it's not concentrating, wonders what's going on. For 10 seconds, comes back. Totally gets it right, absolutely, and then carries on. So not only do they have this way of seeing things very fast, they can remember it for at least 10 seconds. And there might be lots of evolutionary reasons why this is the case that we can't go into now. But the main point is that there are certain things that chimpanzees can do that are better than us, involving numbers, the memory of numbers. Now, I went all around the world, and when I went to Japan to see the chimpanzees, I was probably the first guy to go on like a maths tour of Japan. I wanted to see anything to do with numbers and digits. And I learned that even though we think that maths is the same all over the world because 1 and 1 is 2 everywhere, our approach to maths and the cultural resonance is very, very different. And sometimes even the most simplest way, and I think it's good to think about this because it makes us it challenges some of our own preconceptions about what maths is and what numbers are, where they come from. The most obvious one is tallying. I brought up in the UK, and you tally like this. 1, 2, 3, 4, 5. Obvious. Surely the simplest way. Surely they've been doing this since we were sort of cavemen tallying in caves. And no one does it any other way. But that's wrong. I don't know if there are any South Americans in the audience, or non-Venezuelan South Americans, because Venezuelans do it like this, because the Venezuelans kind of do everything like America. If you're not a Venezuelan South American, this is how you tally. 1, 2, 3, 4, 5. Which actually is a much, much better way than the way we do it. Because here, 3 and 4 is always different. You're never going to confuse it. Whereas, as I said before, 3 and 4 you would confuse it, because at 4 you have to start counting the lines. Now, so if you see a bunch of guys in Brazil playing dominoes, that's how they're counting their scores. In the Far East, though, in Japan, I'll see if there are any Japanese, Chinese, or Korean people in the audience. If you are, be quiet. Because this is how you tally in these countries. 1. Any guess where the next one's going to come from? From there. 2, 3, 4, 5. Is that really confusing and complicated and designed to turn people off counting? Actually, it's beautiful because what it means, that is the kanji character for correct. So it's almost like a haiku. It's a way of kind of containing, sort of mixing words and numbers together. And there's something rather sort of delightful about it. And if you don't believe me, the next time you go to a Chinese restaurant or a sushi place in Soho, ask for sort of 5 beers and the waiter will mark it like that, and it's totally true. I mean, I didn't believe it and I asked myself, and it's a little party trick. Whenever you go to, that's how they tally. Now, I saw lots of different people in Japan, and one of the most fun people I met was this guy here, Akagi. And he's the guy who, I wouldn't say invented, he sort of reinvented Sudoku, but probably the most important guy in the history of Sudoku. Sudoku was actually invented in the late 70s by an amateur puzzle maker in America. And it went in a small American puzzle magazine, but only a few times and no one took any notice. And then Akagi in the early 80s was trying to start a Japanese puzzle magazine, saw this American puzzle magazine, most of it was word puzzles, couldn't understand anything about it, about those ones, saw the number one, thought it was brilliant. So he adapted it, and now the givens in a Sudoku are all parallel, a bit like kind of crosswords, and he coined the phrase, I think he registered it, Sudoku, which means the number appears only once, and then it became a bit of a hit in Japan. And then since it came to Europe about 5 years ago and around the rest of the world, he's become quite wealthy. And he says, I'm not a mathematician, I'm more of a kind of numbers impresario, a kind of showman. And he loves gambling, and he was saying, he's in his 50s, he looks a lot younger. He said, thank God I didn't make all my money when I was in my 30s and 40s. I would have spent it all on geisha girls. And he's like the least sort of nerdy numbers guy you could, especially sort of Japanese guy you would ever expect to meet. And what I loved about him is that wherever he saw, when he saw numbers, he just was making games and having fun with them. And this is what he told me his latest hobby was: taking pictures of Japanese car number plates. I don't know if anyone here can maybe see why he might want to. This would be a good Google question for, these number plates are mathematically interesting. Well, it's because they're lines in the times table. 3 times 5 is 15, and 4 times 1 is 4. So actually there are 81 different types of registration license plate in Japan, and he was going around, and wherever he saw one, if it's on the motorway in a car park, he would just take its picture, and his idea was to have an exhibition of the times tables as seen on car license plates. And I thought that was just sort of brilliant, and you don't need to be a kind of maths genius to appreciate the sort of the beauty and the simplicity in that. That in Japan, probably the greatest way that their approach to maths and numbers is different to, in the UK and in America, certainly, is in the presence of the abacus. Now, this is an abacus. An abacus is a counting machine, or a calculating machine. Probably, it's really the oldest kind of calculating machine that there is. And virtually all cultures that count have similar things. Sometimes they don't make them into mechanical objects. They're just lines, and you have sort of, say, pebbles on a counter. Well, in fact, that's where the word counter comes from. You'd have little counting things. And the abacus, the Japanese abacus called the soroban has 5 beads per rod, so there are 10 positions per rod, so they represent the numbers from 0 to 9. It should be horizontal, so there's no, gravity isn't working. And at the top, you can either, the bead can either be at the top or at the bottom, likewise at the bottom. So you start with 0, these 4 here would be 0, 1, you see the one at the bottom goes up, 2 would go up, 3 goes up, 4 goes up, and 5, they all go down, and the top one goes down to go 5. So it's kind of like a little base 5 within the base 10 there. Now, you do not need, and once you get good at the abacus, it's very easy to do addition and subtraction, because just by putting in the sum, you've done the addition already. And once, multiplication is essentially a little bit more complicated addition. So you can do addition, square roots, division, all that really, really quickly using an abacus. And in fact, up until the dawn of the pocket calculator in Japan, and from Russia eastwards, actually, everyone would learn a calculator. Everyone would learn to calculate using an abacus. And actually, I've brought this item on here, which came out in Japan in the 70s when the pocket calculator was becoming popular. And you might think that this abacus calculator is you do the sum on the abacus, and then you just check that you're right with the calculator. But obviously, it was completely the other way around, because they didn't trust this. So they would do it here, and they would just check on the abacus just to see if they got it right. Now, the phrase for reading, writing, arithmetic in Japanese is yomi, kaki, soroban, reading, writing, soroban. So it's very kind of culturally, it's in their culture. And even though you do not need to use an abacus in daily life at all, you don't even need to use it for the school math syllabus, still 1 million Japanese kids every year study the abacus at about 20,000 abacus schools, or kind of they're called jukus, where it's sort of after-school clubs. And Japan has this kind of tradition of these jukus for other things, after-school clubs. So Monday you might want to do violin practice, Tuesday baseball, Wednesday soroban. And I went to one to see what they did. And this is basically what goes on in a soroban school. You learn to calculate using the abacus. It's very competitive, and you can get speeds and when you get sort of good at it. And because it's competitive, the awards that you get are just like a martial art. So if you get good, you get your dans, and it goes up in dans. So just like in karate or whatever, I don't know anything about martial arts, but I know that they use dans. They use dans in the abacus. And I went to a competition, because they have lots of competitions. This is a regional competition. There were maybe a couple of hundred kids doing it, and it was several hours on their Sunday. And this is them the person's reading out sums, and they're calculating as fast as possible. This is the sums being read out. And this is what you win, these wonderful winged figures holding sort of golden soroban. Absolutely fantastic. Now, why do people learn the soroban? And why would you want to calculate really fast mentally if you don't really need to? And I asked this guy, Yoji Miyamoto, who this is his kind of group of soroban pupils, why? And he just looked at me, he just really didn't understand the question. And he said, well, why would you ever want to run for 26 miles? But people do. He said, there's this idea that why not practice something that the body, the human, can do as best as possible, and running and sport. What about the kind of the brain muscle as well, to kind of practice that? And also I could see that the kids were they're really having fun. There's something about learning with the abacus, there's something kind of visceral about the counting that makes people enjoy it a lot more. Now, I was kind of fascinated by the soroban, and then Yoji Miyamoto made me more fascinated by telling me about something called handson. Handson is, if you can do the abacus really well, after a while, you don't need to have a physical abacus anymore to do the same calculations, because you can visualize the abacus in your brain, right? So I said, well, what do you mean? He said, okay, and he got one of his top pupils and just said something. It was, I don't know, 57 times 321, and the guy just gave the answer. And I said, well, what's going on in your brain? He said, yeah, I have like 8 rows, 8 columns with the beads in my brain. I was just like moving them around. And it's absolutely amazing. And Yoji Miyamoto decided to sort of, because there's something very Japanese about it, he wanted to kind of publicize it more. So he thought, why don't I think up a game, some kind of counting task, which the only way of solving it is using handson. So if you were to say, 25 times 26, say, millions of ways you could solve it. You could stick it in Google, for example. You could go on the beach and a line of 25 and 26 pebbles. You could use an abacus, you could handson, you could do all these things. So that's not good. That task, just saying something. And then he had this idea, why don't I have a computer screen flashing digits so fast that you can't write them down and work out a task like that? So he invented this game called Flash handson, which I'm going to show you now, which flashes digits incredibly fast. And the idea is, in this game here particularly, to add them all up. So what you're going to see is 15 digits, and they're all 3-digit numbers. So like 221 is a 3-digit number. 15 of them in 3 seconds. That's 5 per second. And the purpose, or the object, is to count them and say the answer, to add them all up. 15 digits, 3 seconds. Yeah, you got it right. So what's going on is he can't remember any of the intermediate sums. He's got a blank abacus. He sees the first one, he just sees it instantly as a shape on the abacus. He sees the next one, and instantly he just adds it. And he keeps on adding, and he's like reading the printout at the end. And you might, when I heard about it, I said, oh, can I film it? And there's like, I filmed it here. And I thought that maybe they had to do it 10 times to get it right the first time, or maybe, but this was the very first time they did it completely right. So, the guys can do it, and it is amazing. Now, I was pretty impressed by this, but not as impressed as I was for the next thing you can do with an abacus. When I was trying to understand a little bit about why we can do this, about sort of the neurology of it, or the neuroscience of it, they say in Japan, and not that much research has been done on this, but they basically say, right brain, normal maths, left brain, left brain, normal maths, right brain, abacus. What they mean is that our left side of the brain, the left hemisphere, tends to be used for linguistic programming, so language, numbers, counting, all that kind of thing. And the right side of the brain is the visuospatial skills that we have. So normally we use the left side of the brain to do maths. But with the abacus, it's using the other side of the brain. So what this means is that you could do the abacus or flash handson whilst, your left side of the brain is still free. So they designed this test, which is to do flash handson whilst playing a language game at the same time. All right? So what I'm going to show you now is it's 2 10-year-old girls. One of them is actually the daughter of the teacher. They're going to be doing, I think it's 30 digits in 20 seconds. And whilst playing this Japanese word game called shiritori, which is, the first person says shiritori, the next person has to start a word, say a word that begins with ri, the last syllable of the previous word. And the person after that has to say a word beginning with the last syllable of the previous word. Very kind of common. We have things like that, but with letters rather than syllables. So this is two girls playing shiritori whilst counting. Yeah, they got it completely right. And that was the first time that I filmed them. So it's absolutely fascinating. So the abacus is basically the oldest way to calculate, but it's still, in some ways, the most versatile and also the littlest understood. Now, very quickly, the final section I'm going to have to rush through because I realize I'm running out of time. I went to all these very glamorous places: Japan, India, Phoenix, Arizona, etc. But I also went to some less glamorous places, Braintree in Essex. And the reason I went to Braintree is that I discovered that Britain's second largest collection of slide rules is in Braintree. And as a journalist and having to make all this sort of exciting, you kind of want something that's quite funny, it's got a comic potential. And I thought this is going to be hilarious because the slide rule has got to be like the world's, the reputation is like the most nerdy thing ever. So I was intending to think that it was going to be easy gags. But when I got there, I realized I kind of fell in love with mathematical instruments because the slide rule, which I guess I'm looking at the ages of people here, most people here probably don't even know what slide rule is. A slide rule uses logarithms to become, you can do multiplications and division and square roots very easily by sliding two log scales against each other. And when the logarithms were invented about 400 years ago, a couple of decades later, the slide rule was invented, and it totally revolutionized science. Straight away, you could do long, complicated calculations very quickly. And probably every single great invention of the last 350, 400 years required a slide rule, right up until, you can almost date it, it's like August 1974 when Sinclair's pocket calculator came out and no one needed them anymore. So nothing has been so dominant and then died so quickly. And actually, I can remember, and also from movies in the sort of 50s and 60s, the slide rule was this sort of really quite boring, like two sticks, like really sort of dull that people would have in like their top pocket. But actually, for hundreds of years, their sort of beautiful ones were made, and every industry, every trade had their own type of slide rule. And when I was, seeing that this guy's house, these collections, they were gorgeous. And quickly, this one is from the 1890s, which the log scales, you pull them out, and that's called Thatcher's calculating instrument. This one here was the most amazing. Also from the 1890s, it's called Professor Fuller's calculator. And the scales were on a helix running to about 45 feet. So you could do a calculation with this to 5 decimal places. So normally most slide rules, they're only analog because you're looking on the stick to see where something goes. You get about 3 decimal places. And 5 decimal places for most types of engineering is more than enough. So it's amazing to think that something could could calculate within seconds a complicated sum to 5 decimal places 120 years ago. There's also the Holden Count Lex, and I actually brought one, which is a sort of debonair person's slide rule, which you'd have maybe like this, like a kind of pocket watch, and where the slide rules, the log scales are circular. And when I was there, I was just getting so falling in love with these machines, and actually the collection of mathematical instruments is like huge growth area. You look on eBay, there are all these things there worth hundreds of pounds. I saw this item here, which looks like a hand grenade or a pepper grinder. And what it is actually, it's not a slide rule, it's the only digital pocket mechanical calculator ever made. So Pascal, 400 odd years ago, had this dream to mechanize calculating. and he invented the Pascaline, which is sort of the very first one. And then Leibniz has its step reckoner, and there's this whole history of people mechanizing counting. That's where the word kind of number crunching comes from. And then there's the Victorian age, and also in the early 20th century, or right to the mid-20th century, people would have these big desk sort of machines that would do all this calculating for them. Then in the 1930s, Kurt Starck, an Austrian, had this idea for this new sort of systems, engineering system, that he can make a pocket-sized one. And it took him 20 years to work out exactly how to do it, and he was imprisoned for some of that time as a prisoner in Buchenwald concentration camp. And he was half Jewish, so he was going to be killed. But because the Germans knew he was working on this, they didn't kill him, and they said, if you invent this, we will present it to the Führer, and you'll be declared Aryan, and you will survive. And he didn't do it quite in time. We don't know if he actually did, but didn't want to tell them, but he'd almost completed it by the time he was liberated by the Russians. Then, in the years after the war, worked out how to do it, tried to get funding. The only people who could get funding was the Duchy of Liechtenstein. So he moved to Liechtenstein, and for basically up until the late 60s, this was made. And I brought one here, which is the most sort of beautiful, beautiful thing. It basically can do multiplications and divisions, all those things, and you put the number in, and then you grind it around. If anyone wants to have a look afterwards, I'll show it. But what is sort of interesting is that this, in a sense, was the zenith of the dreams of mechanical calculation. It was pocket-sized, sort of beautiful engineering, beautiful sort of, but it's sort of the end of the road of a way of thought, because then calculating came all about information and electronics and computers and you guys and stuff like this. So this is quite nice, a sort of, it's like a historical relic, a kind of fossil almost, of the dreams for hundreds of years of the mechanization of calculation. Now, we're just going to finish here, because at the beginning of the talk, I said, now hopefully it will come, if all numbers were listed alphabetically, what number would come second?
8 billion.
Correct. Correct. Or sometimes people, but in French. 5 billion, I think. I think, yes. Or 1,000,000,008, but some people disagree that it should be 1,000,000,008. So, finally, I just want to say that I've got the survey out at the moment. I'm trying to find out what's the world's favorite number. And I've got this website, which is here, favoritenumber.net. And so far, I've had about 25,000 votes from numbers from all over the world, from virtually every country. And so please, if you do, I'm trying to do a study on the emotional connection we have to numbers. If you do have a favorite number, or even if you don't, go on there and say, yes, I do, this is what it is, or don't. And, tweet it and share it with all your friends, because next year, hopefully, I'll have the results. So that's me, and thank you very much for listening.
Thank you very much, Alex, or maybe I should call you Alexander. I think we've got just a few minutes for questions. So does anyone have a question for Alex?
What is your favorite number?
Well, that's the whole thing. I don't have a favorite number. And I would give these talks when my book came out, and people would always put their hand up and say, what's your favorite number? And I thought they were just winding me up, because it's a really stupid thing to have, until I realized that I was in a minority of not having a favorite number. And that's, in a sense, what has given me this sort of impetus, because I'm really fascinated by the fact that people can have favorite numbers, because surely they're all the same. How can you have this emotional connection to something which is so impersonal?
But you have a favorite color, don't you?
Yes, but color.
No idea.
Yes, but a color definitely gives you an emotional reaction. Like red makes angry, green is comforting. Why would a number be more comforting or not than another? And then I kind of realized when I was asking these questions, if you were, people tend to choose numbers below 20, especially under 10. Odds more than evens, which is interesting, and primes more than non-primes. Now, why is this? Lots of sort of theories. And most people, the reason for their favorite number is the day they were born, right? But only if you were born on a low prime. If you were born, like me, on the 22nd, you're very unlikely to choose 22 as a favorite number. So I think that had I been born on the 7th or the 13th or the 11th, that would be my favorite number. But this is a long discussion, and I'll come back and tell you the answers next year.
Could the chimpanzee Could the chimpanzees have beaten the humans for physiological reasons rather than mental capabilities?
Well, what do you mean? Could
So
they?
maybe they focus much faster with their eyes, or
Yeah, I mean, it's the reason why they can do that is going to be that it's much more useful in the wild to have those instant reactions. But I mean, I'm not sure. Is an instant reaction a neurological thing or is it a physiological thing? I don't know enough about.
both?
Yeah, I'm not a neuroscientist, but yeah.
Maybe I can ask a question myself. When you met the guy who had reinvented Sudoku and also
Yeah.
shows of the number plates, you said he was like the least nerdy mathematician or person interested in maths you'll ever meet.
Yeah.
Why do you think it is that there is this kind of association with maths as a nerdy pastime, interest, etc., within society?
Well, it is, I discovered, only really in cultures like, especially Britain, when there is, I don't know, we don't value mathematical skills the way they're valued in other countries. But even in, say, France and Germany, it's quite common. There are a lot more women do science, even in those countries. It's something about the kind of Anglo-Saxon approach that I think it's cultural, but I also think it's changing. And I think that whereas before the word nerd, you'd never say, well, I'm a nerd. That's very negative, very pejorative. Now it's, hey, I'm a geek. Everyone says I'm a geek. It's kind of cool to be a geek. You know, geeks make lots of money and do interesting things in a way that they never were seen as doing that, say, in the 1970s. Yeah?
There's this legend about either Euler or Gauss actually using a human calculator to aid him. Do you know this?
Yes, that's true. That's true. He's called Zacharias Daze. And one thing which is interesting about numbers as well, when numbers, so these Arabic numerals came in about the 13th century to Europe, and it took a few hundred years for them to become dominant. And when they were, all of a sudden, some people were able to have these amazing numerical skills, the sort of idiot savant type. And these people were probably what now we would call sort of Asperger's cases or sort of strong autistics or whatever. But yes, there were some people who have this amazing facility with numbers. And one of them, the most famous one, was Zacharias Daze, who was employed by Euler, actually, was it either Euler or maybe Gauss, where he calculated pi to 200 places, which was the most that was done at the time. And he did a table of factors up to about 8 million. It was just unbelievable. And still now, you can get people who have this amazing ability with numbers from nowhere. And in fact, I'm flying next week to America, and one of the people I'm going to meet is a guy who's got Asperger's, and he's a taxi driver from Tucson, but he's the world's best square rooter. You can kill him any number, and he can get it square root. And he just can, and he always has been able to do that. So these sort of skills, which now, you know, he's a cab driver. If he'd been around in Gauss's day, he might have been working for Gauss, earning lots of money.
Yeah, but like another side question about it, like, well, Gauss or Euler, whoever that was, like, he didn't abandon math to start being like a better calculator. So do you think that actual pure calculation is just like a pointless hobby, like compared to actual math?
Yeah, it's got nothing to. There are lots of great mathematicians that got terrible mental arithmetic, and the ability to be good at mental arithmetic is not really anything to do with the ability to be good at maths. You know, maths values other things. You know, deductive reasoning, creativity, sort of conceptual things. But yeah, and in fact, CERN were the last people. You know, where they've got the Large Hadron Collider, were the last people to use a human calculator. And it was up until the 70s, a guy called Wim Klein, a Dutch guy, and he was used to do the calculations that they were needing there. And then, you know, after the 70s, computers came in and didn't need it anymore. So there's a kind of tradition of the human calculator.
Okay, we probably have time for one more question. There is one more.
So you compared the various tallying techniques, and you looked at the abacus and said that, you know, that's very popular. Are there any other calculating techniques that are particularly easy to understand that we should be teaching our kids instead of the way we do arithmetic right now?
the most interesting thing about how to teach kids, which I hadn't realized, is also to do in Japan, and it's about how they learn the times table. So the times tables in Japan, and I think in China as well, where you go to China, it's called the kuku, because ku is 9, so it's the 9 nines. And you say it exactly as you do here. So we'll start 1, 1 is 1, 2, 1 is 2, 3, 1 is 3. But they sometimes, like a number can, in Japanese, one can be in and it can be ichi, 2 things. So the word that you use within the times tables is chosen to make it scan better. And sometimes the word is actually changed. So ha is 8. Ha ha 8 8 is changed to ha pa because it rolls off the tongue better. So the children are taught the times tables as if they are a nursery rhyme with a kind of musicality to them, and they're actually taught them before they're taught really what they mean. And this means that, one, it's really fun learning the times tables. It's a bit like a rap, and I went into a school and the kids love sort of almost singing the times tables. And it seems to sink deeper. So when I was talking to my interpreter, and she was saying, yeah, when I have to do, say, 6 times 7, I remember the line in the music of the cuckoo about 6 times 7 is 6 times 7 is 42, and then I say 42. So it's this idea that language is being used to make maths easier. The sort of marriage between maths and language is kind of helping the maths and helping the language, whereas here they're sort of, keep themselves to themselves. Yeah.
Cool. Thank you very much, Alex, for coming in to talk to us. We have some little
fantastic.
gifts for you.
Thank you.
And I'm sure everyone is very happy that you came in.
Thank you.